Matter and life are all around us. All of them are made of atoms, tiny particles. We see an infinite diversity of matter and life. They are all made up by combinations of about 100 kinds of atoms. Now, these atoms are made of protons, neutrons, and electrons. And protons and neutrons are made of even smaller particles called elementary particles. Here at KEK, we study the world of matter and life by using large experimental apparatuses called particle accelerators. Welcome to KEK, the High Energy Accelerator Research Organization. KEK is a research laboratory with particle accelerators. With particle accelerators, we experiment and research on the origin of the universe, unknowns in matter, and secrets of life. We have two campuses, one in Tsukuba City and the other in Tokai Village. At the Tsukuba campus, we accelerate electrons, and at the Tokai campus, protons. Both campuses host a variety of apparatuses and facilities for experiments. KEK is organized by 2 research institutes and 2 research laboratories. Institute of Particle and Nuclear Studies. Here we study elementary particles and nuclei. We are working to uncover the origin and working of the whole material world, the universe. Theorists and experimentalists work together to advance the research at KEK. Institute of Materials Structure Science. Here we study the structure of the material. We use synchrotron radiation, neutron beams, muon beams, and slow positron beams, all produced by particle accelerators at KEK. Accelerator Laboratory. We build particle accelerators and operate them. Particle accelerators are the basis of all the research at KEK. Applied Research Laboratory is KEK's backbone that support all such particle accelerators and research. We take care of cryogenics and superconducting technologies and support mechanical engineering. We manage the radiation safety in a large computer system, and we carry out cutting-edge R&D in all these fields for future particle accelerators. KEK is one of the inter-university research organizations in Japan. We host large-scale facilities which are difficult for individual universities to maintain. KEK is also a founding member of the Graduate University for Advanced Studies to accept graduate students. KEK is a center of global research activities. A large number of scientists visit KEK. We have many programs of international cooperation. One such collaboration is with CERN in Switzerland. Now, let us introduce some major facilities at KEK to you. At the Tsukuba campus, we have an Injector Linac. With this Linac, we accelerate electron beams. With it, we also produce beams of positron, that is, antiparticle of electron. These beams are brought to 3 storage rings. 2 rings are for synchrotron radiation facilities. The 3rd ring, with a circumference of 3 kilometers, is for studies of particle physics. Representative facilities at KEK: KEK Accelerator, Belle Detector. These 2 facilities, the largest of their kind in Japan, are collectively called the B Factory. The B factory is for colliding the electron and the positron, antiparticle of electron. In the collisions, we produce an enormous number of B mesons and tau particles. The Belle Detector measures these particles. By analyzing those reactions in details by using computers, we confirmed the violation of CP symmetry in B mesons, difference between particle and antiparticle. Violation of CP symmetry is a very important phenomenon. We believe that it is responsible for why our universe is the way it is. In the Big Bang, we believe that the same number of particles and antiparticles were produced. However, in the present universe, we see only matter, no antimatter. This difference between particles and antiparticles, violation of CP symmetry, is a big mystery of the universe. The B factory was an experimental facility to tackle this mystery. As a result, Dr. Kobayashi and Dr. Masukawa, who proposed a theory which explains why CP violation occurs, were awarded the Nobel Prize in Physics in 2008. Right now, the KEK Accelerator and the Belle Detector are undergoing a major upgrade. At the Photon Factory, we do research in a different way. Suppose we have accelerated electrons to nearly the speed of light. When we change the direction of motion of such electrons, light is emitted. It is called synchrotron radiation. With this synchrotron radiation, the Photon Factory examines structures of material and organisms' components at the atomic level. Like a radiograph, by using X-rays, we can see structures that cannot be seen with visible light. X-ray with a short wavelength is a powerful tool. With it, we can examine the content of material and its fine structure without destroying it. With the knowledge of the material structures, we can advance our understanding of the properties of a variety of materials and complex working of living organisms. Dr. Ada Yonat is an Israeli physicist who was awarded the Nobel Prize in Chemistry in 2009 for her study of the structure and function of the ribosome. The Photon Factory provided Dr. Yonat with an experimental facility to perform an early stage of her study. By elucidating the detailed three-dimensional structure of a protein, we can deepen our understanding of mechanisms in life phenomena. By knowing how proteins and pharmaceutical agents interact with each other, we can develop new drugs too. For solving environmental and energy issues, we have to develop better battery materials and catalysts. This is a major effort. Studies on the relationship between the structure and function of materials at the atomic level help this effort. At the Tokai campus, we operate the J-PARC Center with our partner, the Japan Atomic Energy Agency. J-PARC is a facility which produces high-intensity proton beams. Neutrons and muons are produced by irradiating targets with a proton beam. With these neutrons and muons at the Material and Life Science Experimental Facility of J-PARC, we study the structure and function of materials. With neutron and muon beams, we can easily observe light atoms such as hydrogen and lithium. This is not easy with synchrotron radiation, so they complement each other. Our understanding of materials at the atomic and molecular levels is improved by using different types of beams. At the Hadron Experimental Facility, we study elementary particles and nuclei by using hadrons. Hadrons are particles that are composed of multiple quarks. In addition, J-PARC can produce neutrino beams. Neutrino beams from J-PARC are directed toward the Super-Kamiokande detector in Gifu Prefecture, 300 kilometers away from the Tokai campus. With these, we study the properties of neutrinos. At KEK, we are working on the particle accelerators of tomorrow and the future for further advancing science and technologies. On the B Factory, we are upgrading the KEK into Super-Kekubi and Belle into Belle 2. Super-Kekubi will be a 40 times more powerful apparatus. At J-PARC, we are upgrading the facilities and instruments to accumulate a larger amount of data with improved quality. For Synchrotron radiation research, we are developing a new accelerator, Energy Recovery Linac. And in addition, we are conducting research and development of accelerator technologies for the International Linear Collider, a next-generation electron-positron collider for an unprecedented energy scale. Researchers from all over the world come to work at KEK. They are watching the journey of tiny particles, electrons and protons. At KEK, we are trying to uncover the mysteries of the universe, material, life, to find out what they are and how they work. And our research continues on day and night for the future of science, the future of our generation, and generations to come.